Hello, chemists. This is Ms. Placino, and you are watching Screencast 11.1 on factors affecting rate. In today's lesson, we're going to talk about the different factors or variables that we can control that are going to change the rate or speed at which a chemical reaction or physical change occurs. So what we're going to start today is a discussion on chemical kinetics. Kinetics is just a branch of chemistry that's concerned with the rate or speed at which chemical reactions occur. Sometimes you might want a reaction to occur more quickly, sometimes you might need it to occur more slowly, and for our purposes there are 6 different factors that we're going to be able to control that ultimately will change or potentially can change the speed of a chemical reaction. But before we get into what those factors are, I want to talk a little bit about what needs to happen between our reactant molecules in order to get an actual reaction. And if you stop and think about it, in order for the molecules, the reactants, to actually react with each other, they have to come in contact with one another. More specifically, we need collisions. Our reactant molecules have to hit each other. And when they do hit each other, collisions can be classified in one of 2 ways. We can call them effective collisions, and these are the type of collisions that occur and produce the desired product. So they make the thing that we're looking for. We can also have ineffective collisions, and these are collisions between our reactant molecules that do not produce the desired product. In Reagents chemistry, most of our reactions are pretty simple and straightforward. So if you aren't getting the reaction to occur, it's probably because you have ineffective collisions, so just no reaction is occurring. As you get to larger and more complicated molecules, like in organic chemistry, ineffective collisions can also be collisions that yield an undesired product. So instead of making one molecule, the reactants have reacted in a different manner than you wanted them to, and you've produced a different molecule. Again, not something that really happens a lot at the Reagents chemistry level because we're working with small, simple compounds and molecules, but as things become larger and more complicated, you can yield products that you didn't really want. So in order for reactions to occur, we need effective collisions. So you might be wondering what makes a collision effective, and it turns out there are really 2 factors. Collisions have to occur at the proper speed and orientation. So when we're talking about speed, that just means that molecules must collide with enough energy. They've got to be moving fast enough to start breaking those bonds that exist between the reactant molecules. You can kind of think about our potential energy diagrams. I'll draw one here. Happens to be an exothermic reaction. We need to provide enough energy to our reactant molecules so that they can get into the transition state. And that's where we have bonds breaking and starting to reform and to ultimately get to the products. And if we don't put enough energy in, we don't smash those molecules together at a fast enough speed, they'll never reach the transition state, and therefore a reaction will never occur. Collisions also have to occur at the proper orientation. So let's take a look at that. So here's just a simple example between ethene. This is carbon and hydrogen-based compound with a double bond, and this looks like probably HCl. In collision 1, this is going to yield our desired product. This is our effective collision. We have to make sure that the hydrogen part of this molecule is pointing into the double bond. We don't get what we want if, again, I believe this is supposed to be representative of chlorine. If the chlorine atom's pointing at it, we don't get the reaction we want. If the chlorine atom is pointed at, instead of the double bond, one of the carbon atoms, we don't get the reaction we want. It's another ineffective collision. Whether it doesn't yield the product we want or just simply won't react, we don't really know in this case, but we're not getting an effective collision. Same thing with collision number 4. We've got the hydrogen aimed at another hydrogen instead of the double bond, and again, no effective collision. So in order for reactions to occur more quickly, we need more collisions. And if you think about it, speed and orientation, which one of these is going to be easiest for us to control? Yeah, it's definitely the speed of the molecules. It's going to be all but impossible to get in there and try to manipulate the orientation of the molecules. We can't see them. We have no way of working with one molecule at a time. So all we can do is try to make collisions happen more frequently. And then statistics are in our favor. You have more collisions, you have more chances for effective collisions, and ultimately a faster reaction. All right, so if you look at your workbook, you've got a place to brainstorm some different factors that can affect the rate of a chemical reaction, or a physical change for that matter. And there are 6 different ways. So why don't you pause the video, see if you can brainstorm a couple different ways that you can impact the rate of a chemical reaction, and then we'll go through and we'll talk about them. All right, let's check these out. So the first factor affecting rate I've come up with is temperature. Hopefully this is one you've thought about too. It's a direct relationship. As temperature increases, generally speaking, the faster the reaction rate will be. If you think about why this occurs, think about the molecular motion. If you've got something in a hot water bath, I guess this is not going to be the best hot water bath because I don't even see a flame under there. There, we'll draw one in. And an ice bath, what's true about the speed of the water molecules in both of these cases? Well, in the hot water bath, molecules of water are going to be moving faster. They've got greater kinetic energy. In the cold water bath, or the ice bath, molecules of water are going to be moving more slowly. We know that due to differences in temperature. If the goal is to get more collisions, if you've got water molecules moving around a lot more quickly, the odds of collisions occurring is definitely higher than if they're moving more slowly. So if we increase the temperature, molecules move faster and are more likely to collide with sufficient energy to get a reaction to occur. Next we have changing the pressure, which we can affect by changing the volume. Make a note, this applies to gases only. Liquids and solids are relatively unchanged by changes in pressure or volume. So this really is for gases only. This is another direct relationship. As the pressure increases, the reaction rate increases. And let's think about why. Here we've got the same number of molecules in a large volume. So this would also be like a low, a low pressure. And in this case, they're in a smaller volume, so we have a high pressure. The odds of collisions occurring are much greater the higher the pressure is. There's just less space for the molecules to move around, so there's a better chance of them running into each other. More chances for collisions, better chance that you're going to have a faster reaction rate. Up next we have surface area. Pressure applies to gases only. Surface area applies to solids only. You can't really change the surface area of a gas or a liquid. So this is a direct relationship. Again, you have more surface area, you see an increased reaction rate. Well, think about why. Look at the picture. In order for a reaction to occur, it's got to come in contact. It's got to collide your two reactant molecules. So if you think about like a big cube of sugar in your coffee or tea versus granulated sugar, you probably know from experience that granulated sugar will dissolve more quickly. That's because, we'll just think about this very two-dimensionally. In order for any of this stuff in the middle to react, we need the stuff along the surface to react. So there's a limited number of molecules that are in contact. We continue with our coffee and sugar analogy with the coffee. If you look at increased surface area, now I have more molecules of sugar exposed, so more of them can react with the water or the coffee, whatever you'd like to think of it as. So as I give just more locations for reaction to occur, I've increased my surface area, I have a better chance of collisions and therefore a faster reaction. Hopefully you're noticing a pattern. We're talking about, in these 3 cases so far, just find a way to increase the number of collisions that can occur. This is not going to necessarily, with the exception of kinetic energy change, temperature change the speed, but we're just increasing the odds of a collision occurring. All right, up next we've got concentration of reactants. This is another direct relationship. As concentration increases, reaction rate increases as well. Here we have low concentration up top, high concentration below, And I think it's pretty self-explanatory just by looking at the pictures. If the red and blue dots represent our reactants, there is a much greater chance of them colliding in the high concentration circle at the bottom, just because there's not as much space for them to move. I guess it's the same amount of space, but because you have more particles in there, each molecule is not going to have the same amount of space, so they're going to hit each other more frequently, more collisions, faster reaction rate. Nature of reactants. This was one that is sometimes a little harder for people to understand. Molecules that have bonds that are easier to break react faster. And you definitely want to make a note of this. Aqueous ionic compounds react the fastest. If you think about what we do in lab, a lot of times we're taking aqueous solutions of ionic compounds and we're running reactions. The reason for that is they react almost immediately. Like your precipitation reactions happen very, very quickly in the aqueous phase. When we do something like burning magnesium in air, we have Mg as the solid. We're reacting with N2. We can also react that with O2. And we end up producing a white solid. Now, if you just think about it in terms of what the atmosphere is made up of, you might think that we mostly make magnesium nitride because the atmosphere is roughly 70 or so % nitrogen. And we'd make a much smaller amount of magnesium oxide because the atmosphere is only like 28% oxygen. But if you take a look at the nature of the reactants, we have N2 and O2 up here. We didn't really talk about bond energy in this course, but using a little bit of common sense, what do you think is going to be easier to break, a double bond or a triple bond? Hopefully you're thinking double bond. Excuse me. So when magnesium combusts in the atmosphere, it's a lot easier for it to react with oxygen because it just has to break through a double bond, instead of with nitrogen, where you have to break through a triple bond. So this is what we mean by nature of reactants. If you've got molecules that have easier bonds to break, they're going to react faster, usually because it just requires less energy to break through them. You kind of think about somebody like chopping through a pile of wood. It's going to be relatively easy to break one board, but as you continue to add boards, it's going to take more and more energy, and it's going to be more difficult to get through them all. So that's what we're talking about with nature of reactants, usually looking at bonds. All right, last but not least is the addition of a catalyst. You might remember talking about catalysts in biology class. A catalyst is always going to increase the rate of a reaction, and it does this by lowering the activation energy required. It's just kind of worth pointing out that it does not change the overall reaction. By definition, a catalyst is present in small amounts. It gets used up and then regenerated as the reaction progresses. So here's just kind of a simplified example of what that would look like. The blue potential energy diagram is showing us what the reaction looks like uncatalyzed. The red line is showing us what happens when you catalyze the reaction. So we see a substantial drop in activation energy. What does not change, however, as we go from reactants to products, is delta H. Catalysts do not change the delta H of the reaction. All they do is lower the activation energy. So the reaction itself does not fundamentally change. We just see a lowering in activation energy as the catalyst usually just helps to stabilize the transition state and make it a little bit easier to get to that point. All right, that wraps it up for today. There are some practice problems getting you to think about how to speed up or slow down the rate of a reaction. Definitely make sure you understand how this works. Hope you found this helpful, and thanks for tuning in.